it's an interesting situation where there is one paradigm that's the best for language, and then another paradigm that seems to be the best for pretty much anything else. It's an interesting situation because I don't think it can last. I believe that we don't tolerate complexity in the long run.
Today we're talking with Sander Dieleman. Sander is a research scientist at DeepMind, where he focuses on diffusion models for generative media, image generation, video, audio, music, and more. In addition to being an amazing researcher, Sander is also one of the world's best interpreters of diffusion research. So I remember when I first got interested in diffusion and I was asking different AI researchers, what should I go read to really understand this stuff? Everyone pointed me towards Sander's blog. The blog is excellent. It contains really deep, intuitive explanations of all of the key ideas in diffusion, and also goes into some sort of emerging frontier topics as well. Today, we're both going to talk about Sander's work and his interpretations of key events in the history of diffusion.
I remember the first blog post of yours that I ever came across, which was this Perspectives on Diffusion blog post, where you kind of lay out 11 or 12 different ways of interpreting diffusion models. And it reminded me of this article by William Thurston, who is this low-dimensional topologist who won a Fields Medal. But he had this article a while ago that sort of talks about many different interpretations of the gradient. And he sort of says, you can think about it geometrically, it's the normal vector to the tangent plane. You could sort of think about it, sort of maximization guide. It sort of tells you what direction to go in to increase fastest. He sort of had this point that all these different interpretations are useful for different things. Maybe my first question about that post is, which of those 11 or 12 interpretations you find yourself coming back to most often when you sort of think about diffusion models? What's the framing that you come back to most frequently?
Well, that's an interesting one. As you point out, they're all useful, right? That's why it's such a useful thing to have all these different perspectives and be able to kind of derive different insights from them and then combine those. I would say the most important one is probably the idea of diffusion models as estimating expectations. Which is maybe not the most sort of flashy one that was in there.
Yeah.
But it's one that's, I think, very sort of instrumental in understanding what these models are actually doing. Like the fact that they're estimating conditional expectations and not sort of, you supervise them during training, you supervise them to predict a particular image, let's say. But really what you want the model to estimate is the expectation over all possible images that could have given rise to a particular noisy image. And through the wonders of machine learning and mean squared error and all these things, that kind of ends up learning exactly that expectation. But I think that understanding is kind of fundamental in really sort of intuitively understanding how diffusion models work.
Maybe especially during sampling, because I think that another thing, I remember sort of being surprised initially when you run these things and you get these very fuzzy images, sort of why should the prediction be the sort of fuzzy image? But I remember you sort of had a nice explainer of that where, in reality, you sort of have to average across all possible images that could have sort of produced the noised version that you see. Is that what you sort of mean by the expectation interpretation?
Exactly. Yeah. And it wasn't in that blog post, but in another blog post, I sort of tried to represent this geometrically. Like you can look at this as sort of moving around in the input space. You can represent that space in 2D, which is kind of restrictive because, of course, the input space of images is much higher dimensional in practice. You have tons of pixels and 3 color channels. But in 2D, you can kind of visualize things, and then you can see that really what the diffusion model is giving you, what it's predicting at any point in the space is the direction that you should move the input in to make it more likely under the distribution that you're trying to model.
Yeah. Maybe this is something to come back to later, but then I wonder how you think about these sort of like single step, these sort of reverse diffusion processes like consistency models or something like that, do actually go to some specific sample from the data distribution as opposed to something that's sort of more averaged or smoothed out.
Yeah, I think that's this kind of understanding of diffusion models as estimating expectations is fundamental in understanding how consistency models are different because they don't do that. And it's interesting because a consistency model essentially learns this sort of mapping between samples from a noise distribution and samples from a data distribution. And that mapping is sort of optimal in some sense. It seems like diffusion models are sort of learning that same mapping, right? They're actually like training a diffusion model seems to be the easiest thing that we have right now to uncover that mapping. But then once you have that mapping, you can distill it into something like a consistency model that just gives you that mapping in one go, in one forward pass in the ideal case. And it's interesting that it's so much harder to learn that mapping directly. Like, it seems like it's a necessary intermediate step to train a diffusion model first, at least for now, to be able to really learn that optimal mapping.
Yeah, this is kind of an aside, but I was asking Yang Song about that paper. And, for me, I sort of thought about the consistency distillation as kind of the main thing, because, you sort of have this pre-trained diffusion model. It's really nice that you can sort of impose this consistency property on top of it. But I was sort of surprised that he said that, like, the part that he was most excited about was sort of training consistency models from scratch, which he almost regarded as sort of like a new type of generative model, and it sort of should be thought of differently, which I thought was interesting.
Yeah, I mean, I kind of agree with that. It's a different way of characterizing that same transport. If you can make it work in a way, it's a more useful way, because you can, you get the mapping in one step. You don't have to simulate a process to recover the mapping, which is nice in theory. In practice, of course, it is probably more complicated to learn that mapping from scratch. And so far, it seems that, like, going through diffusion model training or flow matching, we want to call it, seems to be the most practical and most scalable way to get there, to uncover.
Well, maybe going back to that blog post, across those different interpretations, are there any ones that you feel are particularly underrated? Ones that people should maybe pay more attention to, or where there's some insight that's sort of less well appreciated or less pervasive?
I was very excited about the spectral autoregression implementation, right? This idea of diffusion as actually performing an approximate kind of autoregression, but in frequency space rather than in pixel space. As you probably know, I wrote a more detailed blog post on that specific perspective more recently, and that seems to have sort of given that idea some traction. But I didn't come up with the idea. There's actually a really nice paper from Severi Rissanen is the lead author, I believe, where they kind of it was actually a paper about using blurring as a corruption process in generative modeling rather than adding Gaussian noise. Then they also make this observation that actually diffusion models are kind of implicitly doing a very similar thing, because as you add more noise to an image, you're actually obscuring more and more of the high frequency content, leaving only the low frequency content sort of observable. That's a paper where I sort of first got exposed to this idea, and I thought, well, this is actually really elegant and really insightful, and I think more people should know about this. And so that's why I ended up writing a blog post about that one.
Super interesting. Well, I wanted to ask you two things about the auto-regressive interpretation. One is, I remember that in that original blog post, you sort of sketched out this argument, we sort of put things in the frequency domain. There's this, sort of surprising and interesting property that natural images sort of follow this power law, and that, you can sort of reason that Gaussian noise looks like it should just be a flat line because it's the same across all frequencies. And you draw these sort of stylized curves about sort of what it ought to look like as you sort of add Gaussian noise at different noise levels for images, and you sort of get these bent curves. It seems to me like it was sort of very reasoned from first principles. And then later you do the work in this later blog post of actually producing these charts for specific images, and they look exactly like that.
It's a surprise to me.
Yeah, that's exactly what I was going to ask, which was sort of how much you knew it was going to come out that way, how much it was sort of a surprise, maybe just sort of how closely it matched might have been surprising.
I didn't quite expect the theory to play out, like to be so close to practice. And in hindsight, it's not entirely surprising, because so I'm visualizing all these image spectra in one dimension, right? I'm kind of collapsing them to one dimension, because technically images are two-dimensional objects. So their spectra are also two-dimensional, but you can kind of average them across all possible directions. And then you get this, this radially averaged power spectral density that I talk about in the blog post. And that averaging operation is, of course, smoothing out a lot of the sort of the random fluctuations that you would get. And so you get something that looks fairly smooth, even if you calculate it only across a few images. I think I used a batch of 128 images or something for the blog post. Even if you use like 16 images, it already looks very sort of theoretical in a sense, because there's a lot of noise there. Incidentally, when you then try to do the same with audio, which I also do in the blog post, see those curves are a lot noisier because you don't have that averaging effect, because a 1D spectrum It's a 1D signal, so you get a 1D spectrum.
Super interesting. The other thing I wanted to ask about this is, as I was thinking about the sort of autoregressive interpretation for, let's say like image diffusion, for instance, it feels like there's this kind of ordering to it where you start by producing sort of the low frequency components, and then you autoregressively produce, sort of medium frequency ones, then you produce sort of high frequency ones after that. But there's sort of this natural order. And when I think about that in comparison with, say, sort of discrete next token prediction, autoregression, it doesn't feel to me like it has the same sort of ordering structure in a way. The token that I produce sort of at the beginning sort of feels like it carries roughly the same signal as a token that I produce later. There's not some way of interpreting one as sort of like low frequency or high frequency, at least naively as I think about it from the outside. And so I was curious how you think about that. If, there's lots of things I could imagine, maybe this is just something that's different between the two. Maybe there is some sort of interesting way to sort of apply this for discrete tokens. Just curious how you think about that ordering characteristic.
Yeah, the ordering thing is interesting. So if we just talk about language for a second, like just in a context of language modeling, the way autoregressive models work is essentially by taking a joint distribution over sequences and then factorizing that into sequential conditionals, right? The conditional distributions that give you the next token given all previous tokens. And then you can just multiply all those together, and then the laws of probability say that that gives you the joint distribution. But you can actually do that in any order, right? You can choose the order as you see fit. And of course, when we're doing language modeling, because we already have the sort of sequence representation, there's a very natural order, which is just that inherent order of the sequence. And I think like people have done experiments on this and actually found that if you sort of arbitrarily change this order, actually modeling becomes harder. You could just jumble up the entire sequence and then order it, and then model it in that order. But that's actually a harder learning problem. There's some sort of inductive bias in the models that we use for these tasks that is helpful when we use the correct order, so to speak, which is the original order. Now, if you look at images, you want to use a sort of the language modeling paradigm to model images, which you can do simply by tokenizing the images into a sequence of discrete tokens. Then the question becomes, what should the order of the tokens be? Because now there isn't a sort of predetermined best order to turn a 2D object like an image into a 1D object like a sequence. And often what people do is sort of the simplest thing, which is raster scan order, which is just the way the pixels are stored on a computer, like let's just use that. But there are probably smarter ways to do it that are maybe more hierarchical. And so one option would be to go from low frequency to high frequency, which is incidentally something that is done in the JPEG format, like the typical compression format that we use for images, kind of implicitly does this at a block level, within 8x8 blocks of pixels. The information is kind of stored from low frequency to high. And so that's why I think it's interesting that when you look at diffusion models from this perspective, they're actually doing a kind of a soft version of this. It's not as rigorous, let's say, as in the discrete autoregressive case, but there is clearly this process where the low frequencies are getting modeled first, and then the high frequencies are getting modeled conditioned on the low frequency information that has already been filled.
I think it's interesting that we kind of have these two different feeling generation, sort of schemes, right? So we have autoregression sort of works for these discrete tokens. We have diffusion for things like images. I sort of think of you as one of the people who've tried most to sort of bridge these two ways of generating things. What's your long-term prediction? Do we feel like these just still end up being two different paradigms that we keep forever into the future? Do you think that there's some grand unified, generative model that will give us both back? What do you sort of think happens? Because it sort of seems strange that we have these two very successful paradigms that work in different domains.
Yeah, I agree. I mean, it's an interesting sort of situation where there is one paradigm that's the best for language, and then another paradigm that seems to be the best for pretty much anything else. Everything else is a diffusion model now, but somehow language is still decidedly, an autoregressive affair. I think that's interesting. And I've asked myself, why is this? And I've written in my blog about why I think diffusion is such an exceptionally good match for natural image modeling. And there's a few reasons, and some of those may apply to language, some of those may not. But it's an interesting situation because I don't think it can last. I believe that, we don't tolerate complexity in the long run. The things that I always think back about, what was coming out in terms of papers while I was doing my PhD, and which of that stuff do we still use today? the ReLU, residual connections, these very simple ideas that you can explain in one paragraph almost. Those are the things, but they're still very effective, right? And those are the things that stick. And the more complex stuff that people were doing back then, is kind of forgotten. And so that makes me think like there's going to be this pressure to unify these two modeling paradigms, because we are moving towards multimodal models, right? Right now, there's a lot of language models, there's text to image models, there's text to video models, but these are starting to merge together, right? We're starting to get language models that understand and are able to generate images, for example. Currently, that seems to require kind of grafting these two modeling paradigms together in a way that isn't always the most elegant. It's interesting from a research perspective, but I think it's a lot of complexity that in the longer run will not be warranted. And currently, I would say, like for images in particular, there's sort of a clear advantage to diffusion models in terms of the trade-off between cost and quality, both for training and for sampling. But as we scale everything up, I would expect that cost differential to become less and less important. Eventually, we might end up in a situation where it's really just easier to just tokenize everything, turn everything into discrete token sequences, just use the autoregressive transformer paradigm that we know and love, and just use it for everything. Even if that means we're paying a slight cost in terms of image quality, just the fact that we're able to integrate everything so easily might actually start being more important. That's one possible outcome. Another possible outcome is that we finally figure out how to efficiently do diffusion for language in a way that's competitive with the autoregressive paradigm. And then maybe we can all train multimodal diffusion models instead. But I don't know which one it's going to be.
Yeah, that's what I was going to ask, is because, it sort of seems like diffusion has won in so many domains. Language is the last one to sort of conquer. I remember you had another blog post specifically on language diffusion models almost 2 years ago now. I remember you sort of ended on this note of saying, there's a lot of interesting ideas here, but we sort of haven't reached the point. They're really competitive with autoregressive methods. I guess I wanted to hear what's happened since then, and if that's, sort of updated your optimism or pessimism in some way. Sort of how do you think about diffusion models today?
I've been very happy to see that people haven't given up on the idea. So at the time when I wrote this blog post, I had done some work on diffusion models for language. And I'd kind of wrapped up this project to work on sort of our, at DeepMind, our flagship text to image and text to video models and text to music as well. I was kind of wrapping that up. And then, but obviously still keeping an interest in this idea of trying to use diffusion for language. And I've been very happy to see that, there's been a lot of papers, there's been a lot of work trying to make this work, and we've gotten closer, but I don't think we're there yet. It's like, I still haven't seen sort of diffusion language models at the scale that we have typical autoregressive models right now. Like, there's a Llama 70B model. There isn't a 70B diffusion language model yet that's out there. Or that's even described in a paper. We're still kind of working towards that. But I guess also there's this effect of, it's harder to get resources for this kind of more experimental stuff, especially at scale, which may be holding things back. So maybe it's just a question of someone having the guts to do it. Maybe there isn't really any technical barrier anymore. But yeah, there's definitely been some interesting innovations. It's also very interesting to me to see the resurgence of discrete masked diffusion as a kind of paradigm for language modeling. Because when I was working in this space, my perspective was always that, okay, diffusion works really well in continuous space, so maybe we should just embed everything in continuous space if we're going to do diffusion. And the mass diffusion approach is kind of the complete opposite, which is basically it's almost like autoregression, but you allow any order of generation, right? And including generating multiple tokens at the same time. So it's kind of more in between the two paradigms in a sense. And there have been sort of several papers that drew attention to this again, simultaneously, contemporaneously as well. And it's just been really interesting to see.
Yeah, that was one thing I wanted to ask you about, which is that it seems like sort of one way of interpreting what's going on with these masked language diffusion models is that you're sort of forcing each step in the reverse process to, sort of be fully represented as, an actual bunch of tokens, as opposed to being able to sort of keep some kind of superposition between different states as you go back, which seems like it could be quite useful to have that, this idea of, I don't know exactly what this token should be yet. And I sort of want to keep it, somewhere in between, two possible things that it could be. So it seems in some ways that you're giving something up with sort of masked diffusion approaches but maybe in practice, it still works. I'd just be curious your take on that.
Yeah, that was my feeling as well. So I was really convinced that somehow you need to be able to represent these superpositions of possible outcomes in the intermediate steps of the reverse diffusion process, right? Because it's such a, like if you compare it to continuous distribution, the distribution of tokens in a text is so spiky, so so sharp. And so I thought if we have a continuous space, then our intermediate sort of embedding vectors that correspond to the different tokens, like the intermediate embedding vectors could be kind of linear combinations of different possible embeddings. And that could represent uncertainty about which embedding we might end up in. And my intuition was that would be important. But so far, the results that are coming out are proving me wrong, essentially, right? They're basically saying, actually, you don't need that. You can make hard decisions even during the diffusion process and still get really good results.
Maybe switching gears a little bit on sort of the history of the field. So I think I remember, I'm not sure if this is your first blog post on diffusion, but the one that I remember was you published a post on the sort of denoising autoencoder interpretation. And you lay out a little bit of the history at that point, which is sort of say some of these ideas have been swirling around for a while for diffusion models. So Joshua had that paper in 2015. Apo had that score matching paper even earlier. But it kind of wasn't until 2019, 2020, maybe with DDPM and then the Yangsong Stefano paper that sort of diffusion really caught on as this paradigm. At least that's my perception from the outside. So I just wanted to ask your take kind of during this period where, by some measures, we had this early diffusion model. It sort of maybe there was 5 years of GANs between 2015 and 2019. What was it that kind of made diffusion models really take off around that, 2020 period? And, sort of what did it feel like at that time?
Yeah, that's a very good point. So I have been doing generative modeling of audiovisual media, let's say, since about 2016, like very, very shortly after I joined DeepMind. That's what I sort of wanted to work on. That's what I started to work on. At the time, it wasn't really cool. It wasn't really something that a lot of people were interested in. But, I was still very happy that I was able to do that kind of research here. And it wasn't, as you said, until maybe 2020 or something that things really started taking off. I think specifically what was missing in sort of these earlier interpretations of like denoising as generative modeling was this idea of annealing, right? This idea of starting at a very high noise level and then sort of gradually decreasing it as you proceed through the generation process. And that key idea kind of came up in both Yangsong's paper and then also in the DDPM paper. That was sort of important to start making it work at, I guess, what was then called large scale, trying to make it work on things like ImageNet. That was kind of an essential ingredient for that. Another really important discovery was guidance, right? First classifier guidance and then classifier free guidance really sort of amped up the capabilities of these models. Like even relatively small models were then suddenly able to produce fairly high quality images. And that was kind of surprising to me that worked so well. And actually to this day, so it's actually very interesting. Like often when I explain this to people, I have to go back to some of the earlier papers, like the Glide paper from OpenAI, which is one of the first diffusion-based text to image models. Like those are the examples that I use to show people, here's what the impact of guidance is. Because ever since then, people just use guidance and they never turn it off anymore. So you can't really see just how bad the model actually is if you turn off guidance. Like you'd be surprised. A lot of these state-of-the-art diffusion models just really don't work that well if you don't have guidance. Yeah,
it's like the idea is so much in the groundwater that it's hard to imagine not having it. Well, maybe two things related to that. So one, we recorded the interview with Yangsong maybe, I don't know, a week or so ago. And I had asked him about this and he said something that was sort of surprising to me, which was that people didn't think that score matching would work because, for a variety of reasons. It seems like you're throwing away a bunch of global information. It also just seems like it's hard to propagate signal. It's sort of this low density regions problem that Yangsong talks about in that paper, where it's just you have these regions that are just not very dense. And so I sort of had asked like what actually changed things or what sort of made them work. And it seems like being able to perturb all of the points and sort of doing diffusion at these multiple noise levels is really the thing that made this idea work, which feels to me like I didn't appreciate just how important that was in making all of this work until until I'd sort of heard it from him. But it sort of seems like doing that was sort of a big part of the story.
Yeah. That's also what I took away from his original paper back in 2019. It's like, oh, okay, that's what you need to do to make score matching work. Because I knew about score matching because way back during my PhD, I had spent a lot of time working on restricted Boltzmann machines. They were a model that was sort of popular early 2010s in the context of deep learning, because at the time we weren't really able to train deep networks end to end. We had to pre-train them layer by layer. And restricted Boltzmann machines are one way to do that. So I've been looking at that. And then some people suggested, oh, you can actually train these RBMs with score matching. And so that was my first contact with score matching. And I thought, oh, this is actually a super elegant way of doing things, because you have this trick with the gradient and then this partition function that's not tractable. It just drops out. It just disappears.
Yeah.
That's really beautiful. I wish this worked better than it did.
Yeah.
And I sort of moved on from it. And I moved on from RBMs because eventually we didn't need them anymore. We were able to finally train networks deeper than 2 layers without pre-training them layer by layer. And so it was really, really cool to kind of see the resurgence of score matching about 5 years ago now.
What's your intuition for that local to global question too? Because there's this idea of like, so one of the advantages of score matching is we can get rid of that normalizing constant, which is sort of hard to estimate. But on the other hand, it seems like you're losing information by throwing that away, right? So you're giving up some global information about the distribution. And instead you're just focusing on local information. But, somehow in practice, learning that local information really well actually works and generates really, really good samples. So somehow maybe we're not losing that much by giving up the global information. But I don't have a good intuition for why that should be true.
I would argue that we're not really giving it up, but rather we're sort of decomposing it in the sense that we're learning local information, but we're learning local information at these different noise levels. And each of these different noise levels does actually correspond to a different scale. This is literal in the spatial frequency sense, right? Like we talked about before, if you look at images, like the noise levels literally roughly correspond to different spatial frequencies.
Yeah, it's sort of like at any given noise level, you are giving up some global information, but because you have this schedule and you can kind of, sort of push backwards in time, you sort of slowly recover the global picture.
I would say the surprising thing about the diffusion models is that it actually works to then make like 100 predictions in sequence, and somehow you still end up in the data distribution, right? Or not, you don't deviate too far off it. Because usually what happens when you train a single step in a recursive process and then you apply it recursively is that eventually you just veer off the path so far that the input doesn't make sense to the model anymore, right? And this is a problem with autoregressive models as well, right? If it generates a very unlikely token, then from that point on, it might sort of veer off the rails because it hasn't actually seen that token very often in its training data. It's kind of the same thing with diffusion, but somehow this setup with, adding Gaussian noise and then trying to remove it, somehow that seems extra robust against this sort of accumulation of error across multiple predictions.
That's like in the reversed steps for DDPM or something like that. The reason why you add those little Gaussian noise steps is so you don't get, sort of on some weird path that veers off in a bad direction. Is that the...
Yeah, I don't know if it's the reason, strictly speaking, but definitely that's like how I interpret. Like, one thing that people often find is that these sort of stochastic sampling algorithms, which also inject noise in addition to removing it at each step, they seem to work slightly better in many cases than the fully deterministic algorithms, which also exist where you don't add any new noise. And my interpretation of that is that you're kind of covering up the mistakes a little bit by adding that noise back in, which allows you to recurse without worrying too much about introducing accumulating errors.
Got it. Well, going back to guidance, I remember one of the nice things I felt about the score matching approach is it's so easy. It seems so geometrically nice to add conditional information. And you have this really nice blog post on this about the sort of geometric intuition for diffusion guidance, where you write down Bayes' rule, you take logs. The right way of adding this conditional information is sort of you get this extra gradient term that you just, literally can just add to the equation and sort of nudge in that direction. I think it was in that post, you talk a little bit about why classifier-free guidance works so much better than classifier guidance in practice. And I thought that was a really interesting sort of intuition. And it was sort of curious how you thought about that, and maybe to say a little bit more about why that's the case.
Yeah, I mean, it's linked to adversarial examples. When you think about, let's say you have a discriminative machine learning model, let's say a classifier, you give it a certain input, and then it turns out you can slightly perturb that input in a way that's almost or even entirely imperceptible to humans, but it still completely changes the output, right? So these are adversarial examples, and they are typically found by backpropagating through the network into the input and sort of trying to essentially maximize maybe the wrong class label while still staying close to the original input. And so this is kind of what we're doing in classifier guidance as well. We're backpropagating through this network with respect to the input to get the gradient direction that we should follow to make the input image match a particular class better. And that's essentially asking for adversarial examples, right? In a sense, like these models are trained purely to extract information from an input. They are never trained to generate inputs. And so there is just a lot of information in the input that they just completely disregard, right? A lot of information that is not relevant to assigning a class label, but is very relevant perceptually. I'm talking about images in particular here, right? If you look at an image, there's a lot of data there. There's a lot of information, a lot of entropy that is just completely irrelevant to a classifier. And so a classifier will not learn about that. And so if you then backpropagate through that classifier, it's going to do all kinds of weird stuff to that information. And it's just not going to look good. If you use classifier free guidance and you're sort of reusing your generative model to construct that classifier that you need, you're essentially constructing a Bayesian classifier that you then use to do guidance, then by definition, that model kind of understands a lot more about the data and is much more likely to give meaningful gradient directions than a gradient from classifier would.
And why is that? Why is it just because there's so many more things that it has to learn than a classifier model? Just it's not just some finite discrete list of things, but who knows how this text doing?
Yeah, that's pretty much it. And like back in the day, people were observing this as well and finding that they could regularize classifiers by also adding generative losses in addition and things like that. So this is kind of known before, but I guess it took that key insight that you can just construct this classifier from your generative model already, and you don't need a separate classifier, and then people could see the difference. Yeah.
Really interesting. Well, from a historical perspective, I wanted to ask you maybe specifically for image diffusion. What do you sort of think of the key things that happened sort of post 2020, sort of what the waypoints that you would choose? It said maybe these are the papers that sort of had the most surprising results or the ones that updated your beliefs the most, or things that you think were sort of the most important handful of steps that we took over the next few years.
Yeah, I need to think a little bit about that, but like one very obvious one is the elucidating paper, elucidating the design space of diffusion-based generative models by Tero Karas and his colleagues. They're all in Finland at NVIDIA. That paper really is one that I still come back to on a very regular basis, because it's just, it really tries to get to the essence of like what works, what doesn't work, and why, both in terms of sampling and in terms of training. Just get a lot of...
This is the diffusion Bible, right?
That's what I like to call it.
Yeah.
So that one's really nice. I also more recently wrote a blog post about this idea of noise schedules and what actually affects... How do you make diffusion models focus on different aspects of the data, essentially, like different noise levels, which in the case of images corresponds to these different spatial frequencies. And in that context, there was a really nice paper from Der Kingman, Richie Gao, which sort of really goes into this, really sort of analyzing the different things that affect the relative weighting of noise levels and what impact that has on the result. So those are sort of two that were important for me to kind of shape my thinking around this. And then another one is one I already mentioned, the one from Severi Rissanen and colleagues on generative modeling through inverse heat dissipation, because of this analysis, because of this spectral analysis that they applied to the setting for the first time.
Really interesting. Maybe, one area that I wanted to ask you about, you had this Twitter thread a while ago about diffusion models as sort of solving these optimal transport problems. And, I, from the outside, I sort of think some of the interesting things that happened over time were we, there were these score matching papers, and then Yangsong and others developed this sort of differential, sort of a stochastic differential equations perspective. Eventually we get this ODE. We sort of then think about how we have single shot ODE solvers, but how do we sort of, use them in the right way for diffusion? And, in all of these cases, it sort of seems like we're trying to get rid of this iterative reverse time step process and sort of go in a single step. I hadn't heard of or sort of thought of the optimal transport framing as a way of thinking about this problem, but it makes a lot of sense. Yeah, we'd just love to hear how you think about that, and if that is sort of the way you think of the right way of interpreting the actual sort of reverse process for diffusion.
Yeah, I mean, I think there is clearly some underlying mapping that diffusion models learn. People have also found sort of interesting correspondences between, like, if you train a diffusion model on one data set and then you slightly modify the data set and you train a new diffusion model, then those mappings will be similar. So like it always seems to learn approximately the same mapping. So which implies that it is optimal in some sense. And then once you have this mapping, you can do all kinds of cool things with it. You can train consistency models. You can do all kinds of distillation to take advantage of the fact that you now have a way to jump in one step from a noise distribution to the data distribution. So yeah, I really like this perspective. Generally, what does seem to happen at scale is people try to distill these very powerful diffusion models into a single step, and it doesn't really work that well. It seems like just a single step of a neural network that's the same size as a diffusion model just maybe isn't powerful enough to fully capture the nuances of all these of this mapping. But we've been able to get to very few steps, like 4 or 8 steps, with results that look, very, very respectable. And if you want to go lower, then often you have to cut corners somehow, right? You have to decide, okay, maybe it's okay if diversity kind of collapses a little bit. So like, it's okay if I always get the same sample for a given prompt, as long as it looks really good. That's a compromise you can make, and then you can get to fewer steps. But yeah, in general, I think there's clearly sort of a limit to what's possible with a certain amount of computation. And I think that's where diffusion models originally drew their power from, right? That they were this more efficient way to throw a lot of compute at the generative modeling problem without having to spend a ton of compute training as well. So one other perspective that I haven't talked about yet is this perspective of diffusion models as recurrent neural networks, right? This sort of single unit of computation, which is the diffusion neural network that you kind of apply recursively multiple times to a canvas to update it iteratively. And then you could look at that computation graph of this whole operation and sort of unroll it and see that actually is just a deeper version of the same neural network, right? You just have more layers stacked on top of each other. And then the question arises, why are we just not training that network end to end? Yeah, let's train that whole network with backpropagation. The reason is simply that it's too expensive, right? It's if your diffusion model has, say, 20 layers, and then you have 100 sampling steps, then you have a 2,000 layer neural network that you have to backpropagate through. And backpropagation is a serial algorithm, right? You have to go down and then up in a particular order. And that's just expensive. So in that sense, diffusion models are this sort of cheaper way that we found to train these very deep computational graphs. But so one logical conclusion from that, if you draw this out, project this far into the future, is that eventually there might be no point to diffusion models anymore, because we will at some point be able to very efficiently train such deep networks end to end. At least that's what I expect based on what I've seen the past 10, 15 years. When I started my PhD almost 15 years ago now, we were training networks that were 2 layers, maybe 4 at a stretch. Now people routinely train networks with hundreds of layers, and it's not really a problem anymore. So maybe another 10 years down the line, we'll be training networks with 10,000, 100,000 layers. And those will be powerful enough to generate complex distributions in one go. And we might not need this iterative refinement paradigm anymore. Or we might just find that we train such a deep network and then combine that with diffusion or what have you, or autoregression or anything else to make it even more powerful generative process.
Maybe this is sort of related. I know you have a long-standing interest in music generation. Music and video strike me as these domains that are sort of a little bit in between these two paradigms in some way. And it's interesting, at least when I read some of the papers on it, it seems to me like there's less consolidation on the way to do these things? Like, it seems to me like there's quite a lot of consolidation on the way that people do image diffusion, for example, and there's like a fair amount of consolidation on the way that people do language modeling. But, something like music, it has this time component, but at any given, slice, it feels like a diffusion problem, and sort of people wrestle with sort of trying to put things in that shape in different ways. I'm curious if you had some view on where that ends up in the long run. Does it look more like a sequence generation problem where we're generating these slices over time? Again, from the outside, I kind of think of the diffusion transformers paper as like a vote in this direction for video generation. But, the other thing I could imagine is just like trying to diffuse over longer and longer, sort of time samples and just sort of one shot, sort of a longer sample. Curious how you think about it.
Yeah, I think it kind of depends on what you're trying to do. Currently, as you said, like these modalities have sort of characteristics of sequences and also characteristics of other topological structures, like the grid structure of an image. And you can use any modeling paradigm for any topology, but obviously there are better matches that might work better than others. I think it depends on the goal. Like one particular observation here is that it seems like with the sort of diffusion-based approach, because we have this sort of implicit coarse-defined generation, they tend to be really good at sort of capturing structure at all the different scales, all the different levels. Whereas with autoregression, like inherently the learning problem is to first learn the local structure and then learn whatever larger scale structure there is that is helpful to predict that local structure, subject to availability of model capacity, right? At some point, your model capacity runs out and then you can't really learn anymore about how something, 100 tokens back influences your current token. Mm-hmm. It's just not computationally efficient to do so. With these modalities in particular, there are applications where it is useful to be able to generate them real time, for example, especially with audio, but also with video. You might want to generate frame by frame and then immediately show it to the user. And then autoregression is your only option. You can't generate in advance in that setting. So I think that's kind of the choice. That's kind of the trade-off. Like, do you really want to kind of maximize coherence and global structure? Then maybe diffusion over all the axes is the way to do it. But if you want to have, let's say, real-time video generation, maybe it should be autoregressive over time and diffusion in space, or maybe it should be aggressive, or something like that.
Yeah, I mean, it feels like there's sort of this interesting tension, like you were saying earlier, where it feels sort of strange that we would end up using different things for different use cases, because there's just this desire to unify in the long run. But well, maybe the last question I want to ask is areas of research that you think are weird but promising. And what I mean by that is, when you first started working and got interested in diffusion, 10 years ago, it wasn't as the sort of area as well known as it is now. These were sort of ideas that were maybe receiving less attention, but it was very promising to push in this direction. I can imagine the same thing being true. Like, I don't think that diffusion was particularly sort of mainline, I guess is what I would say, in like 2015, 2016.
But there wasn't really that notion of diffusion to begin with. There were, I remember Yasha's paper coming out and reading it, and I think, and then I remember, some of the components like score matching being a thing back then that was sort of, on the edge of what people were exploring. Yeah, like it wasn't really diffusion until 2020, I guess.
Yeah. So that's exactly what I want to ask is, things like that you feel are sort of nascent and they're sort of not part of sort of mainline programs at frontier labs today, but, they're probably worth exploring from a more basic research perspective. They might be the thing that are good projects for a particularly courageous PhD student, things like that.
Yeah, I'm actually not sure if I'm a good person to ask about this, because I was clearly sort of interested in these sort of things 5 years ago, 10 years ago. But then my interest in those kind of started paying off because they became mainstream, right? And so now I'm very much focused on, you could call it like explore, exploit, right? In a sense, I'm now in exploit mode because I'm obviously working on the thing that's mainstream. So that maybe makes it harder for me to be on the lookout for for this sort of more sort of this less mature stuff, you know, like things that still need a few extra breakthroughs or things like that to really land. Yeah, no, I mean, yeah, it's almost, it almost makes you a little bit myopic, right? Because like I'm obviously working with diffusion models sort of day to day. So most of the research that I read is in that area as well. And so, yeah, I might have a bit of a blind spot for this now, actually. I'm not actually sure if there is anything in particular that I can pinpoint where I'm like, that's going to be big in 5 years, maybe.
Yeah. No, I mean, it makes sense. I feel like you got in on the seed round of diffusion, and now it's really paying off. Well, amazing. Sander, thanks so much for sitting down to talk about this. Really enjoyed chatting.